Chapter 5: External and Body-Centered Reference in Haptic Memory. This chapter explores how haptic memory, memory based on touch and movement, uses external and body-centered reference cues to encode and recall spatial information. It investigates the interplay between these two reference systems, supported by neurophysiological evidence and behavioral experiments, and discusses their practical and theoretical implications. Key themes: body-centered and external reference systems. Body-centered reference relates to spatial information encoded relative to the body, such as the location of an object in relation to the hand or midline. External reference relates to spatial information encoded relative to external environmental cues, such as objects or landmarks in the surrounding space. Both systems are integral to haptic memory, often working together to improve spatial accuracy. Studies of the brain and nervous system reveal that different neural pathways are responsible for processing body-centered and external reference cues. Key findings include the somatosensory cortex processes touch-based inputs. The posterior parietal cortex integrates touch and movement with external spatial information. Neural plasticity allows these systems to adapt, particularly in individuals with sensory impairments. Behavioral studies show that people use body-centered cues more effectively when external reference cues are absent or unreliable. However, combining both reference systems leads to greater spatial accuracy, especially in complex tasks. Experiments reveal how these systems interact. Tasks involving reaching for objects show that body-centered references are used initially, while external references refine the movement. Deliberate changes in posture or hand position disrupt body-centered cues, leading to predictable errors. External cues, such as tactile frames or objects, help anchor spatial memory and reduce errors. Practical applications. Designing tools for individuals with visual impairments can benefit from incorporating reliable external reference points such as tactile grids or frames. Training programs for rehabilitation can focus on teaching individuals to effectively use body-centered and external cues. Theoretical contributions. The findings challenge the traditional belief that body-centered references dominate haptic memory. Instead, the interplay between these systems is essential for accurate spatial processing. Disrupting body-centered references. Participants were asked to recall the location of an object after changes in posture, such as tilting the head or shifting the hand's position. Errors increased significantly when body-centered references were disrupted, showing their importance in spatial tasks. Enhancing accuracy with external cues. Providing external tactile frames or objects improved recall accuracy, even when body-centered references were disrupted. Combining reference systems experiments combining both body-centered and external cues demonstrated superior performance compared to using either system alone. Designing accessible spaces. Public spaces for visually impaired individuals can be designed with tactile reference points, such as railings or textured pathways to aid navigation. Educational tools for haptic learning. Tactile learning tools such as raised diagrams or models can incorporate both body-centered and external reference cues to enhance comprehension. Rehabilitation and training. Therapy for individuals with sensory impairments can focus on developing strategies to use both types of reference systems effectively. Chapter 5 highlights the critical role of external and body-centered reference systems in haptic memory and spatial processing. While body-centered references are crucial, the addition of external cues significantly enhances accuracy and reduces errors. The findings provide a deeper understanding of how touch and movement contribute to spatial cognition and have practical implications for designing tools, spaces, and training programs.